So let us now proceed to the topic shear stress. So let me demonstrate that by the slideshow regarding on shear stress. Okay, when you hear shear failure, you probably think of shearing pins or bolts. How do this fail? Shearing pins can be used to fasten together two steel plates. So if we have two uh, plates to be connected, it will be connected by a pin or a bolt or a rivet. Okay, so that is inserted into a holes to connect or fasten these two rivets. With high enough plate forces in opposite directions, if we're going to apply a tensile force on the plate, both ends of the plates, it will cut this pin. Okay, each pin has already sheared into two pieces. So what is the shear area here? Of course, the area of the cut. Okay, so if this is cut along the perpendicular line, we will just use the cross-sectional area of this. Okay, but if the force or the shear force or the cutting force is a diagonal one, we will use the force diagonal to that area and the diagonal area as well for that. Okay, so shear forces are those that tend to cause shear failure. As I have said, a shear failure is a cutting failure on the member. Okay, so here's the failure. We'll cut the member. Okay, so the failure plane for metals will be parallel to the external shear forces. So the internal shear stress. So our variable here is the Greek letter tau is simply the shear force. T is acting on the failure plane divided by the area of the failure plane. By the way, T here should be V. Okay, so we are going to denote our shear force as capital letter V. Okay, so that is the shear force or the tangential force acting on the area. So the shear force that acts on the failure plane is resisted by the strength of materials. Since external force is acting parallel to the failure plane, the internal strength of the material is thought of as its internal friction F. This is the material's reactions to the external force T. So meaning the external force will cause an internal stress, and that is internal stress will tend to cut the section of the body. Okay, so that's it for the shear force. I hope that presentation helps for our topic. Okay, so let us go back to the instructional material. So as we can see here, the formula, as I have said, is a simple stress formula also, but we just have to replace the sigma into tau when we have a tau symbol that refers to shearing stress. And then the force here, instead of P, we are going to replace that by V. V actually is the shear force or tangential force applied. Just the same, we're going to use megapascal PSI or KSI. So we have witnessed this a while ago on how this rivet will be sheared into two. Okay, so these are actually examples of shearing. So most of the time shearing occurs in bolt and plate as well as beam. Okay, as well as in beam. Why is that? Because in beams, force are almost perpendicular to the member. Okay, force are perpendicular to the member. So as an example, let us have a single shear. Why single shear? Because this rivet will be just cut into a single cross section. So for this setup, this is termed as double shear. Why double shear? Because if we're going to apply loading here, there will be two sections that will be cut all over this rivet or bolt. And another type of shear stress is this one. This is what we call punching shear. So basically, this column is connected to this plate, and if we're going to apply a compressive force on this column, the effect on the plate will be punching, or this is what we call punching shear. So what is the punching shear here referring to? Perhaps we can illustrate this in a drawing. Say okay, so we see the illustration. Perhaps we can enlarge this one. So remember that, recalling our knowledge in shearing stress, it is cutting the member. So this is a cutting force actually. So a cutting force. So if this P is applied here, there are shearing stress all over the perimeter of the circle here. So there are series of V there. So if this is the hole, there are shear V all over, or distributed all over the shear area. Okay, so that is the principle. So most of the time, the foundation of a certain structure is associated with this principle. Okay, it is associated with that principle of punching shear. So the key here is we should have a sufficient thickness in order to resist this punching shear, because if our thickness is sufficient enough, it will not just cut this member, okay, or this plate. So what is the shear area here if we are going to use this formula? T is equal to V all over A. So no problem with the V, because V is just equal to the P. Okay, V is just equal to P here in the compressive force in the column. How about the area here? So the area, of course, what is the area that was cut out of that? So the area that was cut out of that is actually the perimeter of the circle times the thickness. Okay, so the shear area is equal to circumference, or the perimeter of the circle, times the thickness. So that's it. So that is the simple illustration of the punching shear. Now, going back to our lesson, the next topic is all about bearing stress. So bearing stress is another type of simple stress wherein the formula is just equal to sigma, or the formula is just sigma is equal to P all over A. So we'll just have to have a subscript B here to indicate that this is a bearing stress and the bearing force, and this is the bearing area. Okay, just the same, we will just use megapascal, PSI, or KSI. So usually in a plate, bearing stress is also present. Okay, aside from the shear stress, the tensile stress, we have also the bearing stress. So the bearing stress is a contact between two surfaces. So what are the material that are in contact here in this setup? Of course, the rivet is in contact with the plate. And if P is applied here, it will generate a bearing stress. Why bearing stress? it will increase the contact between the plate and the rivet or bolt. So, as simple as that. We will just use the bearing area wherein what is the point of contact between the plate and the bolt. So that's the question. So that is simple to calculate. So the bearing area is the contact area between the two surfaces. That is the bearing stress. And if we consider the area of the hole, that is equivalent to what? So the area of the bearing is equal to the contact area is this one, diameter times thickness. So it is diameter times thickness. So to illustrate that, may I just delete this one. If we have the plate, say this is the plate, it's connected by say we are going to connect another plate here. By a bolt. So therefore, if we are going to get the cross section of that one, it is like this. Okay. Okay. So this is the, say this is the plate. There will be a bearing stress between the plate and the bolt. So the contact area is actually this one. So this shaded portion here. Okay. So that shaded portion there is actually what? Half of the circumference supposedly times thickness times this thickness. Okay. So the bearing area is equal to half of the circumference, right, times thickness. But since we are dealing with a small figure here, say in bolts, perhaps it is simplified to use the diameter times the thickness. Okay, so the bearing area is equal to the diameter times thickness instead of using this one. So practically this is the correct one, but since we are dealing with small value, perhaps this perimeter all over 2 would be just equal to diameter. So it is approximately equal to the diameter since we have a small values here. So bearing area is equal to diameter times thickness. Now, to sum up, what are the stresses in plate and bolt? So if we are going to have here a tensile force to be applied on both ends, this force P would tend to elongate the plate. So there is shearing, or think we should have a symbol for that. Say we have sigma in the plate. Okay, sigma in the plate. What kind of sigma? It is in tension. Sigma or tensile stress in the plate. What else? We have shearing stress in the rivet. Okay, shearing stress in the rivet and bearing stress also in the rivet. Okay, so all of the stresses we have learned are actually present in this kind of setup. Again, this is the summary. If we have this setup P, first we have tensile stress in the plate, and then shearing stress in the rivet, and bearing stress also in the rivet. So these are the things that we must have to consider in the design of how many rivets and what how large is the rivet, how many rivets, how large is the rivet in a certain strength conditions of the material. So I hope this illustration helps. So now we are going to have examples. Okay, so we have here problem number 1. What is the force required to punch a 20 mm diameter hole in a plate that is 25 mm thick? The shear strength is 350 meganewton per square meter. So meganewton per square meter is actually megapascal. Okay. So in this solution, of course, simple formula. Tau is equal to V all over A. So we have here the allowable 350 is the allowable or the tau here, and then what is the shear area? We have discussed this a while ago. The shear area for a punching shear is the circumference. Okay, circumference of a circle is pi d times the thickness. Okay, so this shaded portion here is actually the shear area. So out of this, we can easily derive what is the force required in order to punch this 20 mm diameter hole and 25 mm thick. Okay.